The surface of the Earth is broken into sections known as plates. These plates move around the surface of the Earth, and the movement of the plates is called plate tectonics. Where two plates collide, it's known as a convergent boundary. Where they separate, it's known as a divergent boundary. And where they slide against each other, it's known as a conservative boundary. Movement of the plates over geological time has resulted in the formation and destruction of numerous continents. The Earth comprises a crust of solid silicate rocks, a mantle of hot plastic iron silicates, a molten iron outer core, and a solid iron inner core. The process of plate tectonics is primarily driven by convection currents in the mantle. These currents are similar to what we see in a pot of boiling water. However, they occur much slower, with a single convection cycle taking tens to hundreds of millions of years. The convection currents drag the crustal plates around the surface of the Earth. Where the continental plates diverge, a ridge of new igneous material is formed. When the plates collide, the heavier magnesium and iron-rich oceanic plates subduct beneath the lighter felspar and quartz-rich continental plates. The process of subduction at convergent boundaries leads to both the destruction and formation of rocks that we call the rock cycle. The oceanic plates melts as it is subducted into the mantle, creating molten rock under high pressure. Some of this molten rock is forced up into the continental plate to form intrusive or plutonic rock in the crust, or extrusive or volcanic rock at the Earth's surface. Volcanic rocks form from the rapidly cooling magma that erupts or flows out of a volcano. The magma may also cool and form volcanic rock within the defects in the rock mass prior to exiting the ground surface. This forms igneous features such as vertical dikes or horizontal sills. Magma originates in a high pressure and high temperature environment. The volcanic rocks form in a low temperature and low pressure environment. This results in particular volcanic characteristics. As the magma cools rapidly, there is a very limited amount of time for crystals to grow. This results in a rock with a crystal size that is non-visible to the naked eye. If we were to look at a section of the volcanic rock under a microscope, however, we would be able to see the crystalline texture of the rock. Sometimes the magma cools slowly enough for one crystal type to grow to a visible size. These crystals are called phenocrysts. As the pressure on the rock is suddenly relieved as it erupts from a volcano, it is possible for dissolved gases to come out of solution. This is similar to when we open a bottle of soft drink for the first time. With the rock cooling rapidly, these gas bubbles can set into the rock as small voids or holes that we call vesicles. This is very common for volcanic rock that is thrown into the air. An example being pumice, a very light rock that we can find on beaches after it has floated here from the volcanic eruptions in the Pacific. Extrusive igneous rocks vary greatly in their appearance due to their mineral content. The classification of the rocks depends on this mineral content. The most common type of volcanic rock is basalt. Basalt is formed from a relatively low silica content fluid magma. The fluidity of the basalt magma enables it to reach the Earth's surface more easily than other types of magma. Basalt comprises primarily plagioclase felspar and pyroxene. Olivine can also be a significant constituent in basalt. The areas with dark shading in the diagram represent black, or in the case of olivine, dark green minerals. This shows you that you would expect basalt to be a dark rock. If we look at the other side of the diagram, we would expect rock types to be light in colour. A good example of this is rhyolite. Rhyolite is rich in alkali felspar and quartz. Rhyolitic magma is relatively rich in silica and as such resists flow. It is far more common for this magma to remain deep in the crust and to cool slowly to form the intrusive igneous rock granite. When it does reach the surface, it is typically in the form of a very violent volcanic eruption due to the pressure required to get it to the surface. As the magma cools rapidly in an unconfined manner, the magma will typically shrink in on itself. This results in tensile stresses being induced in the partially formed rock. Where those stresses exceed the tensile strength of the material, the rock fails and a vertical joint is formed. We call those joints cooling joints. The formation of cooling joints results in a rock that has a columnar appearance. As engineers, we need to consider the nature of the volcanic rock mass. There may be multiple flows. Each flow may have columnar jointing. This jointing will reduce the overall strength and increase the permeability of the rock mass. The jointing will also allow groundwater and air to access more of the rock mass, allowing for weathering to commence. As the rock is formed as a flow, we can expect the volcanic layer to be variable in thickness and to be irregular. Another important consideration for engineers is the nature of the material below the volcanic rock. The flow would have gone over whatever was at the ground surface at the time of the eruption. In this case, we can see that the basalt was underlain by river gravels and cobbles, material that will have vastly different engineering properties to basalt.